axiomatics, which was done in response to ideas of while, I understand. And in this axiomatics, you take the path of particles and the path of light rays as fundamental structures. And you make an axiomatics of just taking intrinsic notions of path of particles and path of photons, as we say. And if you do such an axiomatics, you end up with a white space. And you need an additional postulate just to get rid of this scale which we discussed. So the white space, the path of particles defines a projective structure, and the path of light ray is a conformal structure. And if you look for the compatibility of a conformal and a projective structure, you end up at a white space. And with an additional postulate, then you get a Riemannian space. So this is a natural habitat of this ETS. Axiomatics is a white space. That was number first example. The second is that if you make a gauge theory of scale transformations, then this would not surprise you. Then you end up with a white space, right? And this has been done. It's also later in the book. We discussed these gauge theories. So there is a very good place for wild geometry in our physics schemes nowadays. So this, what I discussed with the post-Riemannian geometry, found its manifestation in linear connection gamma and metric. Let me just recall some of this. It was then yes, now I wanted to quote from Einstein, but I took my book in my office. In order, shortly before Einstein died, he wrote for a foreword of an Italian book on relativity theory. He wrote something which is, oh, you have it here. Thank you very much.
So you mail me, I print it out.
The essential, I quote, this is a translation of Einstein's statement, which was written in German. It was translated by two collaborators and mine, one native English speaker or Australian English speaker into English. The essential achievement of general relativity, namely to overcome rigid space, that is the inertial frame, is only indirectly connected with the introduction of a Riemannian metric. The direct relevant conceptual element is a displacement field, gamma I KL connection, which represents the infinitesimal displacement of vectors. It is this which replaces the parallelism of spatially arbitrary separated vectors fixed by the inertial frame, that is, the equality of corresponding components by an infinitesimal operation. This makes it possible to construct tensors by differentiation and hence to dispense with the introduction of a rigid space, the inertial frame. In the face of this, it seems to be of secondary importance in some sense that some particular gamma can be deduced from a Riemannian metric. So this is just to underline what Einstein thought. Of course, a lot of people would argue that was Einstein in his old age and you shouldn't believe him, but I still believe him. And I think this is a very beautiful statement, which is exactly on the point. I have to add nothing to that. What I do now is just to introduce the corresponding mathematics. We have a linear connection. Linear connection. Gamma. Did I write it now? Yes, ich sehe calculus gamma alpha beta is equal gamma alpha beta I times dxi. It's a one form. It relates the vector from one point to a neighboring point, so it's certainly along a line, and this is so it must be a one form. This is called linear connection, also sometimes by affine connection. It has 4 times 4 times 4, so 4 times 4 squared equals 64 independent components at pi orbit. You have a co-frame, and could use the frame of the co-frame. I'm using the co-frame, theta alpha. Theta alpha. And out of the co-frame I can define the torsion. Torsion is T alpha equals covariant exterior topology. And I have the curvature R alpha beta is by definition the exterior derivative of the connection alpha beta minus gamma alpha gamma which gamma gamma beta. And I have the Ricci one form, which one form alpha is by definition the interior product with a vector, with a frame vector in beta, the interior product this symbol after all in Latin alpha beta. The Ricci one form has 16 independent components, is no longer symmetric in the arbitrary space with an arbitrary connection. If I have a metric, I can raise the indices of the connection, for instance, gamma alpha beta by definition is gamma alpha gamma times gamma small gamma beta. And I can now define as a difference between the Christoffels and an arbitrary connection. I introduce what I call the distortion one form. Distortion one form, which I separate by n alpha beta. It's just the difference between the connection, independent connection minus Christoffel. And minus gamma little alpha beta. The difference between two connections is always a tensor, so this is a tensor. And I can reconstruct from, I can introduce a non-metricity, we had already that, but now the non-metricity, and we see you have this Q alpha beta equal minus ich sehe covariant derivative of the metric. And then you can easily find that you can reconstruct from the distortion the torsion. This is just simple algebra. Torsion T alpha is distortion in beta alpha which theta beta is a symmetric part of the 2 times the symmetric part of the distortion for an output. And this is a little bit of this. And I have, so let me write out now in components. This is also, I can also do it in Excel form, but here is so that I write it. The connection can then be written as a Christoffel connection, gamma ij a plus 1/2. This is what we had already, dijk minus d plus d, let me spare the indices, plus 1/2 of q ijk minus q plus q is before. It's just for computers. If q is equal to 0, we call it a Riemann-Cartan space. Q is the alpha beta is equal to 0. We call a Riemann-Cartan space. Riemann-Cartan space. Cartan called it a space with Euclidean connections eventually. And Scouten also calls it, so Riemann-Cartan RC, Scouten calls it U in 4 dimensions U4. Now, and this is now coming back to the talk which we have attended earlier. If the curvature tensor R alpha beta is equal to 0, this is for an arbitrary connection, but particularly also valid if you have a Riemann-Cartan space, right? I mean, in your talk, and this is identical to 0, we have a Riemann-Cartan space, and then we can have this, and this is called a teleparallelism. This is in many senses a kind of a degenerate case. Tele means, of course, far parallelism. Tele is just means far in English. Tele is the telephone. You speak to the far. And this teleparallelism, the spaces are often called now Weizenbeck space. Weizenbeck. The name suggested by Hayashi, I believe. Weizenbeck space. And this space was used by Einstein for a unified field theory. Einstein unified field theory of 1929. It's called a theory of teleparallelism. 2 years later he gave it up. And secondly, by Müller, Pellegrini and Gebansky. Since the 1960s, since around 1960, has the gravitational theory, the dualistic theory, where you have matter and gravity and nothing else. So these are the teleparallel theories of gravity. And one can show that these teleparallelism theories of gravity under particular conditions are equivalent to Einstein, but only under particular conditions. With such a geometrical apparatus, Cartan developed 1923 and 24 what we call in the book a skeleton of the Einstein-Cartan theory. The skeleton, what is nowadays called Einstein-Cartan theory, the name suggested. Why a skeleton? Because Cartan had a a good idea, but the theory itself was sort of a failure for reasons which we will know. Cartan apparently started from ideas of the brothers Kossara, A and F Kossara. Kossara, well, they were French engineers. They generalized 1909 the classical continuum of elasticity. Elasticity and also of fluid dynamics, which is really a point continuum, sort of a continuum consisting of points responding with stresses. And what the idea of the Kossarats was also not unprecedented, but they sort of were the first who successfully implemented this idea that if you would at each point have one director or two or three or a frame, right? Then you could also rotate the points, and then you would have a new response. Besides the stress, you would have what they call torque or spin moment stresses. So, and nowadays we call that a Kossara continuum. There are different micromorphic and all types of generalizations of classical continua, but this goes back to the Kossara. So that is basically the idea of a direct continuum. I mean, if you have a spin fluid, for instance, you have such a Kossara continuum. If you have such in superfluid helium-3 in the so-called A phase, you have a superfluid which has a spin in one direction at each point. And so you have such continuum nature. And the idea of the Kossara was in 3 dimensions. I call the indices A and B. You have a symmetric and a stress tensor, but they generalized it to an asymmetric stress tensor, P, A, B. And they newly introduced, or in this context, a field which was earlier suggested by Vogt, 1887, a spin field, S, A, B, C, torque stress, they call it. It's anti-symmetric in A and B. So this is a stress, and this is a torque stress. If you generalize it to space-time, you get an energy momentum, Dij by Friedrich mononomic, and the spin field S I J K equals minus S J by K. So these concepts were developed by the Kossarats, and you have a equilibrium law for stress and for torque in the continuum, and in 4 dimensions you have energy momentum and angular momentum conservation. And this idea was taken by Einstein-Cartan, and he developed a theory which is more general than GR, because he wrote it down in a Riemann-Cartan space. But then he, so the Riemann-Cartan spacetime with a torsion was his conception, but then he made one assumption, namely that the divergence, I mean this is now covariant derivative of P J I J is equal 0 like in general relativity, but this is not true, and then he ran into difficulties and couldn't formulate the theory finally. But this is not true, so the theory failed, and only in 1961 for such a theory the field equations were derived, by Sciama and Kibble. But the geometrical concepts the same, which was not immediately realized. I mean, Sciama-Kibble knew about Cartan, but only vaguely. And this was not translated in English, and I don't know how they were in French anyways, and there were not too much influence by it. So that's, and so Cartan had these ideas and developed a geometry for it and also provided the corresponding currents, the energy momentum and the spin angular momentum current was correctly recognized. The structures were all correctly identified by making an unphysical assumption. You have here in Einstein-Cartan theory Lorentz type forces on the right hand side for consistency. He was not able to formulate the theory. So that's what I call it a skeleton of what nowadays is called the Einstein-Cartan theory.
You mean for Cartan, there's some people who also looking at that in 1887 or 1987?
No, I mean this torque stress was invented by Vogt 1887. This was, at the time, it was recognized mainly by Boltzmann that the symmetry of a stress tensor is an independent axiom. It has nothing to do with the definition of stress, but it's an independent axiom. And then Vogt, who wrote a book on crystal physics and thought about moments and moment distributions, introduced a moment stress in addition to the torque stress. And as soon as you introduce a moment stress, the stress becomes asymmetric. The notion of a stress tensor is not intrinsically related to the symmetry of the stress tensor. The symmetry of the stress tensor just means that you have no moment stresses, or in 4 dimensions the energy momentum tensor is only symmetric if you have no speed. If you have speed, this is no longer. Okay, and so this is a geometry which was prepared, and now I come to the theory of Weil, 1929. In section 5, I'm preparing Dirac electron and Wittich gauge invariance. Dirac electron and Wittich gauge invariance. Well, as in the discussion Beto mentioned earlier, I mean, what was brought in newly in order to make the gauge development possible was Dirac's electron theory, 1928. I mean, that matter is described by a wave function, perhaps was de Broglie in 1922, then 1926 Schrödinger formulated his Schrödinger equation, and then subsequently Pauli wrote down the Schrödinger equation for non-relativistic spin, the Schrödinger-Pauli equation, and then a year later Dirac came up with the electron theory. And this concept of the Dirac electron made it possible for Weil to reformulate his 1918 theory in a new type of theory where he derived the electromagnetic field from the Dirac theory, heuristically derived. So we have a force spinor, psi. We have the gamma matrices, which obey gamma alpha, gamma beta. Symmetric is equal to G alpha beta. Then we have the Dirac equation, I H bar C times gamma alpha, partial alpha. leave the C and the H bar, I put it to 0. For this apply to psi is equal to 0. That's the free Dirac equation. Variables in a variation principle are of course psi, and the Dirac joint is say psi bar is the psi Hermitian conjugate.